Problem 12. Three particles are thrown upward in the uniform electric field. One of them doesn't have any charge. So as you see, the only force acting in it is force of gravity. The other one is positive, so you have force of gravity downwards and electric force in the opposite direction of the electric field as well. So they're in the same direction, and that's why you will have to throw it at a higher speed to reach the same height, which is h. And then when we take a negative charge, we will have to throw it at a slower initial speed in order for it to reach the same distance, because in this case electric force is acting in the direction of the field, which is opposite the force of gravity. So let's look at the first. In the first case we have no charge, so therefore initial kinetic energy is going to turn into potential energy. So I can say mgh equals mv squared over 2. So basically that's the work done by force of gravity, and it leads to the loss of kinetic energy. That's our initial kinetic energy, and this is the work done by force of gravity, which is also potential energy. So we have h from here we can find as v squared over 2g, because we cancel masses, it's the same m. And I can either figure out h, or actually just use gh later on in the formula as 625, which is 25 squared over 2. So the second case, positive charge, since it's positive, it's going to be slowing down, and therefore in order for it to reach the same height, you need to throw it at a higher speed. So since the force is working in it is not just force of gravity but another force, I would not be able to write mgh equals mv squared. So I'm going to say mv squared initial over 2 plus the work of non-conservative force, which in this case is our force electric, the green one, equals mgh, and that's our final amount of energy. So from there, the work of non-conservative force, as I said, that's the work of force electric, is going to be basically the difference between mgh, which is mv squared over 2 initial, and the final, which is right here. So 30 is my initial in this case. 25 gave us mgh in the very beginning, so then I can say that my work done by force electric is half of mass, 30 squared minus 25 squared. So 30 squared minus 25, that's like 900 minus 625, that gives us 275 m over 2. Again, mgh is m 625 over 2, and I can use that later on. So work of electric force, in this case you can see E times H times Q. You could find E if you wanted to. You can find Q, but for now I'm just going to keep this the way it is. That is the work done by my non-conservative force, which is electric force. Later on, as I take a positive charge with the same quantity, the initial velocity can be lower than 30 or even 25, because now my electric force is going to be working in the direction of the field, and it's going to be trying to speed it up, or it can be, you can look at it as trying to work against the force of gravity. But again, since this is a non-conservative force, I can say that my total energy, which is initial plus work of non-conservative force, equals my final energy, which is mgh, because it gets here and stops. So I already found that my work of the non-conservative force from the previous slide is 275 m over 2. Then this 275 m over 2 is my work, equals mgh. So from there I can say that what I'm doing is here is canceling m and also multiplying everything by 2. So that takes care of the denominators on the right and makes 2 gh over here. So multiplying by 2. So then v initial squared, which is this right here, is going to be 2gh minus 275. 2gh, remember I told you I'm going to use later on. Gh by itself is 625 over 2. So then 2gh is going to be 625, and therefore my initial squared, well, square root after this. Initial square is going to be 625 minus 275, and then the actual V is going to be square root of that, which is 18.7. And that's